Hi, my name is William James. I'm from the Welding Engineering and Laser Processing Centre at Cranfield University. My presentation is on the in-process mechanical working of additive manufactured Rene 41, which is sponsored by DSTL in the UK. So the aims and objectives of this study are to understand the effect of in-process working on wire plus arc additive manufactured Rene 41. So to do that, we deposited Rene 41 using interpass peening, and we examined the results. We also wanted to establish best parameters for interpass peening of Rene 41. And to do that, we trialed the peening using 3 different parameters. So to compare the properties of Rene 41 with non-worked material, we used room temperature tensile and hardness testing and microstructural observations. And to recommend process parameters, we analysed the results. So what is WAAM? Well, WAAM is the wire plus arc additive manufacturing process, which is a combination of an electric arc used as a heat source and wire as a feedstock. So we have our substrate plate, we have our electrode, which is our plasma welding torch in this case, as well as our wire feeder, which feeds the wire directly to the torch. In this case, we also have a trailing shield, which is providing extra shielding for our deposited material. So here you can see the flow of gas from the torch, which is also argon, as well as the shielding gas, which is argon. So when we start welding, we'll get a deposited layer. So as this also involves mechanical working, we also have a peening hammer. So the in-process working of deposited material in between layers, we're going to use interpass peening, or machine hammer peening as it's officially known. So what is machine hammer peening? Well, it's a technique where an indenter pin oscillates at a moderate frequency and impacts the workpiece in a spatial pattern. So that's a very complicated way of saying we're going to hammer the deposited material. So as you can see, it's going to oscillate, and as we pass over the deposited layer, we're going to work it, and that we're going to call our peened layer. So here's our experimental setup. So as you can see, we have our KUKA welding robot, which is a 6-axis robot. We have our power source, which is sitting behind there as a plasma welding power source. And we have our wire feeder, which is going to feed our wire, as you can see there, all the way to the welding torch. So the wire actually comes all the way from here, comes down behind the robot, comes here and feeds directly to our torch. And the plasma torch is there, which is inside our local shield, which is providing a local shielding. And we have our substrate plate, which is sitting on the table there. And then on top of our substrate plate, we're building our WAAM wool, which is what we're going to analyse. And then we also have our machine hammer peening tool, which is also attached to the same robot. So here are our process parameters for our additive manufacturing. So we used a plasma arc current of 180 amps, a wire feed speed of 2.4 meters per minute, torch travel speed of 0.36 meters per minute, a torch to work distance of 8 millimeters, and we use an interpass temperature of 170 degrees Celsius, which was an approximate temperature after about 3 minutes of cooling. And we also, the local shielding flow rate, which is the flow rate of shielding from that went into the local shield, is 30 litres per minute of argon. So here is a short time-lapse video of our WAAM plus peening process. So the robot will go down and deposit the first layer from left to right. Then after it's completed that, the robot will turn around so it can use the peening tool rather than the welding equipment, and then go down and peen the deposited layer. And then once it's peened that, it will turn back around to deposit the next layer from right to left. And I'm just checking that everything is going as it should be, and I think some minor adjustments need to be made there. So again, after it's finished welding, the robot will spin around again to use the peening tool. And then it will peen that second layer as well. Here's a quick video of the peening process we used in this study. So the whistling is just to let other lab users know that there's going to be a loud noise shortly. So that's our peening process, and the peening parameters we used was an impact frequency of 36 Hz, and that's the frequency that the peening tool is impacting the top of the deposited layers. And the peening tool used a load of 30 kilograms, which is the load sitting above the peening tool. So out of 3 trials, we varied the travel speed, which we used 18, 36 and 112.5 millimeters per second travel speed, which was the travel speed of the peening tool over the top of the deposited layers. So that gave us an approximate input energy of 4.85, 2.43 and 0.776 joules per millimeters squared. So after our walls were completed, we needed to extract some samples. So we used a short wall approach for this because we only need 3 samples to get a good average for our tensile properties. So as you can see, here's our WAAM wall, which is sitting on top of our substrate plate. We also have 3 axes that we're going to refer to in the following micrographs. So first of all, we have our built direction, BD, which is the height of the wall. And we also have our wall axis, which is the length of the wall. And we also have our through thickness, which is the thickness of the wall. So the wall was a total length of 360 millimeters and an approximate height of 20 millimeters. So we extracted 3 tensile samples per wall in those locations. And we also extracted some material for metallographic analysis. So the heat treatments we used was a standard heat treatment from literature, which included solutionizing at 1065 degrees Celsius for 4 hours, followed by air quenching, and then a further aging at 760 degrees for 16 hours, again followed by air quenching. And you can see a nice picture on the right there of our metallographic samples coming out the furnace post solutionizing. So in terms of results, we compared the room temperature performance of Rene 41 in its various conditions. So to start with, we have the wrought data from literature, which gives you a good indication of what Rene 41 is capable of in its wrought condition. So then we have our as deposited material from a previous study. So we see UTS is roughly 60% of the wrought material. So when this as deposited material is heat treated, we get a 3% increase in the UTS, which is these green lines on the graph. And then when this heat treated material is worked at our lowest input energy, which is our highest peening tool travel speed, we get a 23% increase in our UTS versus the as deposited material. And then again, when this material is worked at our medium input energy, we get a 52% increase versus as deposited material. And then at our highest input energy, which is our slowest peening travel speed, we get a 50% increase versus as deposited material. And you can see that once it gets to the medium speed, the medium input energy, there isn't a great deal to be achieved more by inputting at a higher energy. What you can see though is that yield stress for our medium speed is very close to our wrought performance, which is good to see. What you also see as well is that elastic modulus is also approaching the wrought material as well. The microstructure of our samples. So firstly, we're going to take a look at our heat treated only sample, which is our non-worked condition specimen. So you can see this is in the through thickness build direction axis, which is just a cross section through the thickness. So on the macro, you can start to see our columnar grain structure. And if we zoom in on the very top here, you can see the final deposited layer of material. And you can also start to see some of the dendritic structure of the grains as well, mostly orientated in the build direction. And if we zoom in a bit more, we start to see our grain boundaries here. And again, we see this dendritic structure with secondary dendrite arms. Again, the very last layer, they're orientated slightly differently than the rest of the sample. As you can see further down, dendrites tend to be orientated in the build direction. And if we look at the very bottom of our sample, where the Rene 41 interfaces with our Inconel 718 substrate, you can see the wrought 718 on the bottom for our substrate plate, and where it interfaces with the Rene 41. You can also see a remelt line here, which is where the material has been remelted and deposited as we deposited the next layer. And again, you can see our dendrites as well, orientated in the build direction. And then we also have a nice crack here in the middle of the sample. And at the crack edge, you can see precipitate crack edge, which we'll investigate in the next few slides. So here's our microstructure of our highest energy peened material. So this is the sample which had the highest input energy into it while working. So that's the slowest peening tool travel speed. And again, you can see our columnar grain structure. But when we take a closer look at the top, where you can see our indentation from the peening tool, the dendritic structure is much more disrupted than it was in the non-worked material. And if we look at the bottom of the sample, again you can see our remelt line here, which is showing a bit of an indentation than what it was before, as well as our grain structure as well. So if we compare the two and look at the top of both of the samples together, you can see the clear difference between them in the different texture of the dendrites and the disruption that the peening process has caused. And we look at the middle of the sample, you can see some remelt lines. So there's a remelt line here. And then in the worked material, there's a remelt line here. And again, you can see the disruption in the texture of the microstructure. And then at the very bottom of the sample, it's probably the clearest image to see this, but you've got very straight orientated grains compared to our work material. It's difficult to make out some of these dendrite lines. And then again at the bottom, you can see our nice curvature of our remelt line on probably our first layer here, compared to our worked material, where we've got a nice indentation, as well as the disruption of the grains in the build direction as well. You can see much more orderly in our non-worked material. So then comparing the two samples under the electron microscope, this is very zoomed out at 75 times zoom, but we can see our indentation here again and our non-worked material here. So if we go to 1000 times magnification, there's not a great deal of difference to be observed in either of the materials. And if we zoom in, if we switch to backscatter, you can start to see some of these precipitates, brightly coloured precipitates and also darker coloured ones. They're both very similar in both of the samples, which kind of suggests that there isn't a great deal of difference between them. So again, even further zoomed in at 5000 times now, we can see there isn't a great deal of difference between the formed precipitates in both of the samples. And we also, if we switch to backscatters, we can see our brightly coloured precipitates, indicating heavier elements in these precipitates versus these darker coloured phases. And they're virtually the same in both conditions. So if we look at the EDS data of this sample, you can see already the depletion of nickel in this formed phase here, this brightly coloured one, and you can see the concentration of molybdenum in that phase as well. And then our darker coloured phases, which are these ones, you can see are actually rich in titanium. So if we take a closer look at the composition, we'll look at the base composition first, which is indicated by spectrum C, which is excluding a lot of the precipitates you can see here. Gives us a good base for comparison. So if we look at, first of all, phase A, which is this brightly coloured one, you can see is very rich in molybdenum compared to the base composition, and is also depleted in nickel and slightly depleted in cobalt as well. And then if we look at these darker coloured phases, which is spectrum B on the table, and which is this one here, you can see rich in titanium, which is confirmed by the composition, where we see quite a big increase in the percentage of titanium versus the base composition. So in conclusion, we have the following results for our study. The in-process working increases the performance of Rene 41 by up to 48% versus just the heat-treated only material. And a peening energy density of more than 2.43 joules per millimeter squared doesn't result in any significant benefit for us. So we also found that Rene 41 work hardens quickly, and the micro hardness increases with the work done, which can be seen in the paper. And the interpass peening of Rene 41, as we saw, it disrupts the grain structure typically observed in WAAM, and we saw that quite significant difference in the texture of the material. So we found that in-process working of Rene 41 results in a decreased susceptibility to cracking, because we didn't find any cracks in our worked material. And we think that might be due to the relaxation of the strain introduced during welding. So here are some references if anyone was interested in finding out some more. Thanks for listening, and I hope you enjoyed my presentation. My name's William James, and you can reach me at w.james@cranfield.ac.uk if you'd like to find out some more.